So far this morning, we've seen some pretty game-changing technologies, but of course, it's now time to talk about the glue that binds them all together. But before we do introduce what's new in the latest, greatest iteration of LabVIEW, we wanted to put it all into a little context. So LabVIEW has proven itself time and time again over a long and illustrious career, right from its humble but important beginnings as a tool for automating instrument control, then deployable only on Mac, all the way through to the comprehensive intelligent system design tool that we know today. Now, of course, used in endless application areas and deployable to countless targets. But one man has been there through every step of LabVIEW's incredible journey. That man is Jeff Kodosky. So Jeff's revolutionary vision has guided every evolution of LabVIEW, and it will continue to do so long into the future. Amongst the developer community, Jeff is affectionately referred to as the father of LabVIEW. And to a LabVIEW fanboy like myself, this man is nothing short of a hero. And because Jeff's work has positively and directly impacted the careers of the majority of people in this room, there is no one better placed to talk us through the highlights of LabVIEW's incredible CV and the awesome applications it's enabled. So, as I sidle off to the edge of the stage to enjoy this presentation with you guys, please give a very warm welcome to co-founder of National Instruments and the inventor of LabVIEW, Jeff Kodosky.
Thank you. Good morning. Several years ago, the U.S. National Academy of Engineering, with input from engineering associations worldwide, proposed 14 engineering grand challenges of the 21st century. These challenges span many disciplines, from energy to medicine to the environment, including making solar energy economical, providing access to clean water globally, improving urban infrastructure, making cyberspace secure, and so on. National Instruments has customers around the world working on many aspects of every single one of these grand challenges. And of course, there are many more engineering projects of all types, advancing technology and improving our quality of life. Now, one of the grand challenges is to engineer the tools of discovery. As an example, one of the biggest tools of discovery in the world today is the Large Hadron Collider at CERN. A lot of engineering went into making the LHC, but its basic purpose is to discover new fundamental physics, the discovery of the Higgs boson being the first such achievement. And by the way, LabVIEW played a small but important role in the LHC, helping to keep the protons beams collimated. My background is in science, and I thought it might be interesting today to emphasize this one particular grand challenge, engineering the tools of discovery. Now, our mission at National Instruments is to equip engineers and scientists with the tools to accelerate productivity, innovation, and discovery. So let's look at some examples of scientific research where LabVIEW is accelerating productivity and discovery. LabVIEW's role in scientific research is in designing, building, and running the experimental apparatus. LabVIEW accelerates the research enterprise and the discoveries that follow by making that process faster and more efficient. When we introduced LabVIEW, we were trying to make it easy to automate the use of benchtop instruments in a test environment. It turned out that test engineers were content with programming in BASIC and weren't interested in LabVIEW. And instead, we found scientists and researchers in many fields embracing LabVIEW as the means to accelerate their research productivity. People like Dr. Ira Ramphill, a postdoctorate fellow at the University of California, San Francisco, studying neurosurgical anesthesia in the late 1980s. He was developing electroencephalogram algorithms to assess the effect of anesthetics on the brain when he learned about LabVIEW. He began using LabVIEW 1 because it allowed him to write code and test it much faster than the traditional languages he was fluent in. His work with LabVIEW led to the refinement of his algorithm, validation in the operating room, and ultimately incorporation into computerized EEG monitors. His later work with LabVIEW also led to his discovery, still regarded as seminal, that the spinal cord is a major site of action of general anesthetics. It was the first time a computer system collected physiologic data for a major clinical FDA trial, and it was LabVIEW all the way. Early successes like this were great motivators to the entire development team. If researchers were benefiting so much from a novel but immature tool like LabVIEW 1, imagine what they could accomplish with a higher performance version, something they all sorely wanted and needed. We delivered this in LabVIEW 2 with the Dataflow compiler and much more usable editor. Since those early days, LabVIEW has been used by researchers in many areas, from life sciences and neuroscience to high-energy physics and nanoscale physics to the environment and atmospheric science and many other scientific disciplines. Rapid advances in technology are enabling scientists to gain a deeper understanding of the mechanisms of life, from the molecular level to the cellular level and to the complete organism. We're all familiar with ultrasonic imaging. It's a safe, low-cost, and non-invasive way to capture moving images from deep within the body, and it enjoys widespread application in medical diagnostics. This is my 6th grandchild. She was born in April. Isn't she cute? But ultrasound can be an even more versatile tool when the sound field is more intense and precisely controlled. Researchers at the Institute for Medical Science and Technology at the University of Dundee are using LabVIEW and FlexRio to continuously drive an array of ultrasonic transducers. By varying the phase of the signal to each transducer, particles trapped in the ultrasonic standing wave field can be moved around in real time. The image at the top right shows the ultrasonic pressure field. The darker region at the center and the concentric rings are low pressure areas where particles can be trapped. And the image on the bottom right shows a clump of 10 micron sized particles at the center of the sound field, as well as particles that collected in the first surrounding ring of low pressure. The sonotweezers research will ultimately lead to a low-cost system for non-contact manipulation of live cells, and this will serve many applications in life sciences and medicine. Ultrasound can be used even more aggressively. By focusing high-intensity ultrasound, cancerous tissue can be heated and destroyed without surgery. But one of the difficulties is preventing overtreatment, where healthy tissue gets destroyed as well. Researchers at the University of Oxford are using bubbles to solve this problem. Little bubbles naturally form in the presence of high-amplitude sound waves, and they can actually improve treatment in two ways. On the one hand, the pulsing of the bubbles delivers more heat to the tissue, thus speeding the treatment. And on the other hand, the bubbles have their own acoustic signature, which makes it possible to use them for imaging and monitoring the treatment. The image on the left shows the custom-designed hydrophone array used for capturing the signal from the bubbles, and the image on the right shows the lab setup with high-speed digitizer and FlexRio module, along with LabVIEW software for analyzing and displaying the data. The system is now being used in clinical trials as a better and safer treatment for a difficult form of cancer, namely liver cancer. Physics is the study of matter and energy in the universe, from the behavior of fundamental particles and forces to the bulk properties of matter in solids, liquids, gases, and plasmas. A key tool used by physicists is the particle accelerator. Very high energy accelerators like LHC are used to study the nature of fundamental particles and forces, but lower energy accelerators are used for many other kinds of measurements and are even used in medical applications. The ISIS synchrotron accelerates protons, which are then used to create neutron beams and muon beams, which in turn are used to study atomic and magnetic structure of materials, including superconductors, polymers, thin films, and biomolecules. The proton synchrotron is just the first part of the experimental apparatus at the Rutherford Appleton Laboratory, and its efficient operation is key to supporting this broad-ranging research agenda. A bunch of protons is injected into the synchrotron, makes 12,000 trips around the loop, getting boosted in energy on each revolution, and then exits at 85% the speed of light. This all happens in just 10 milliseconds and is repeated 50 times per second, producing a pulse beam of protons. The main challenge with any accelerator is to deliver a beam as efficiently as possible, and that means minimizing the amount of the beam that's lost to collision with the edge of the vacuum pipe containing the beam. There are 39 beam loss monitors distributed around the circumference of the synchrotron, which can indirectly detect protons striking the edge of the beam pipe. There are also a pair of 40-channel beam profile monitors which measure the intensity versus the horizontal and vertical distance across the beam pipe. Using PXI controllers and digitizers, data can now be acquired over the whole acceleration cycle at double the previous sample rate and 16 times the previous resolution. Monitoring overall beam loss, as well as the position and profile of the beam during acceleration, makes it possible to analyze the behavior and adjust parameters to minimize loss and improve performance. The increased accelerator performance is a key component of the ISIS expansion to better support the downstream research instrumentation. The Earth's climate is changing rapidly today, compared to changes that occurred over geologic time. We need to understand what occurred in the past and what's happening now so that we can make better predictions about future changes, be better prepared to deal with the consequences, and possibly ameliorate some of the negative effects. One major concern is sea level rise due to melting glaciers, particularly on Greenland and Antarctica. Airborne geophysics is a prime tool to explore ice sheets and image subglacial environments and to study associated geological features. The British Antarctic Survey is at the forefront in airborne geophysical surveying, having developed an enhanced platform which combines ice-sounding radar, aeromagnetic, and aerogravity sensors. LabVIEW and PXI were used in the design of a new custom radar system. LabVIEW was used to design the user interface, analyze acquired data, manage system configuration, record the radar ice depth soundings, and provide real-time data display. The ruggedness of the PXI system enabled it to perform flawlessly in sub-zero temperatures and high vibration levels. Recently, the British Antarctic Survey has released a new detailed map of the Antarctic continent, with 2 orders of magnitude more data than previously available. The height and thickness of the ice and the shape of the landscape below are fundamental to modeling the ice sheet. The survey data will enable researchers to accurately assess its current status and model its future behavior. So LabVIEW accelerates scientific research productivity and discovery. As a proxy for estimating the impact of LabVIEW, we can look at the cumulative number of peer-reviewed science papers published by year where the research was assisted by LabVIEW. Google Scholar found approximately 50,000 scientific papers published to date. The graph represents just the scientific papers, not the 100,000 plus engineering papers where LabVIEW is assisting in engineering research and development. It's clear from this graph that the use of LabVIEW in scientific research is accelerating and the overall impact is growing exponentially. Knowledge and understanding of our world is growing faster than ever, and LabVIEW is helping to make this possible. I'd like to close with a brief description of the evolution of our vision at National Instruments. As I mentioned earlier, LabVIEW was conceived as a tool to help automate test and measurement applications. We connected instruments to computers and used the LabVIEW software effectively to create a custom higher-level instrument, a virtual instrument, where the computer controlled the attached instruments, processed and analyzed the data from them, and displayed the results on the computer screen. Over the years, we replaced more and more of the attached instruments with modular plug-in instruments, lowering cost, leveraging the computer's processing power and display graphics, and riding Moore's law to ever greater performance. We're still doing this and will continue to do so. But 2 things happened to broaden our perspective and vision for the future. The first was the introduction of LabVIEW Real-Time. We were persuaded by some visionary customers that our graphical programming for test and measurement was equally applicable to real-time control. And indeed, once we got LabVIEW to run on a real-time operating system, it could run deterministically. The second thing was the introduction of LabVIEW FPGA. We saw the FPGA technology emerging, and thought it would be possible to have LabVIEW run there, but we weren't at all sure how it might be used. Once we had a prototype, though, it was clear just how valuable it could be for precise I/O timing and very high-speed control. And the inherent parallelism in LabVIEW's data flow language is manifestly real parallelism on an FPGA. So now we find that the platform we built has much broader utility than originally envisioned, and we need a new term to describe this expanded scope: graphical system design, using LabVIEW and FPGA-based reconfigurable I/O to design, prototype, and deploy test and measurement systems, real-time control systems, and embedded systems. Graphical system design lets scientists and engineers, the domain experts, explore and prototype new designs in a fraction of the time and effort using traditional tools. The result is increased productivity and accelerated innovation and discovery. We will continue to deliver on our vision to equip scientists and engineers with the tools they need to help solve the important challenges we face today, and to inspire the next generation of innovators to follow in their path and solve tomorrow's challenges. Thank you very much.